This video is an introduction to disaggregated model evaluation and comparison. Throughout the video, we will describe the main concepts of disaggregated evaluation, how these concepts relate to responsible AI approaches of scoring and evaluating a machine learning model, and how they can be used in practice. Let's get started. Evaluating machine learning models is a crucial step in the machine learning lifecycle. The numbers we report at the end of the evaluation guide us through important decisions such as, is this model ready for production? Does it satisfy predefined quality criteria? Or if I have many models at hand, which model should I pick for deployment? One of the most common gaps in evaluation is using aggregated metrics as single score numbers to report model performance. For example, we see these single score numbers being used in the press, in machine learning competitions, or even in research papers, claiming that a given model has, for example, 90% accuracy on a given benchmark. The issue with such aggregated metrics is that they assume uniform model behavior and performance across different input conditions. However, if we look under the hood and slice the training data or the test data on different input conditions, we often find that model performance is far from uniform. In fact, there may be cohorts in the data for which the model has a much lower performance and higher failure rate. In fact, these different regions of the data may also fail for very different reasons. This is why it is important for practitioners to be able to generate and report more granular performance reports that can describe performance in a detailed way. We call these techniques disaggregated model evaluation, and the goal is to report model accuracy performance by highlighting the most common failure modes and how they may be different from cases when the model is actually correct. Let us look at some examples together. A study conducted in 2017 on emotion recognition showed that emotion recognition models at the time had a high accuracy recognizing happiness in children, but that they did very poorly in detecting negative emotions such as fear and anger. Yet another influential case study on the task of gender detection, called Gender Shades, showed that for this task, several APIs had a much lower accuracy for women with a darker skin tone. A follow-up study based on the same data also discovered that the error rate increases 7 times, from 5% to 35%, for women that are not wearing makeup, had short hair or tied hair in the photos, and were not smiling in the photo. In fact, if you go back to your experiments or notebooks, it may be an interesting exercise to run to see if model performance is uniform across different conditions, or if there are such clusters of data where the error rate is a lot higher. These and other examples show that drop in performance for particular regions in the data is an important indicator that needs to be part of the decision-making for deployment. This is because such issues may be exposed in different forms in real-world systems, and they may create safety issues, fairness, or trust concerns. These may become safety issues in the case of a self-driving car that is not able to detect traffic lights, or they may become fairness concerns if the model discriminates against certain population groups. And if safety or fairness are not at risk, lack of reliability for corner cases and unexpected conditions can become a trust issue if the system suddenly fails unexpectedly. At the heart of disaggregated evaluation is the concept of a cohort. The literature has used different terminology for cohorts, such as slices of the data or subgroups, but the concept remains the same. These are subsets of data that are created by adding different filters to the overall test or trained data sets. For example, a cohort on a census dataset may be all individuals whose age is higher than 40 and their residency is in Florida. Or for a medical dataset, it may be all patients whose gender is female and they have diabetes in the list of pre-existing conditions. Based on reporting accuracy on all these different cohorts, yet another measure that is useful to report is performance discrepancy, either as a ratio or difference. Some common forms of discrepancy may be reporting discrepancy of model performance between the whole data versus a cohort of interest, or discrepancy between two cohorts of interest. For instance, we may want to compare model performance in the set of Washington residents versus New York residents. One may also look at interesting or sensitive or important dimensions of data in order to understand discrepancies between different dimensions and at the intersection of those. For example, if gender and age are important dimensions for an application, one may compute the best and worst performance of the model for these different combinations, or the discrepancy between the best and the worst performance as an indicator. A common question for practitioners is how to design these cohorts on the first place. Here are a few guidelines that one can take in consideration during this process. First, cohorts can be created either by using ground truth or automated filters. For example, for tabular data, one can use the very features used in the model to define cohorts. For data that is more in the vision space and that may not have metadata associated with it, it is also possible to aim at generating the metadata with automated methods. For example, in self-driving applications, one may consider to tag the data with the time of the day and create cohorts based on that. This type of tagging can tell us whether it is night or day during the photos and create cohorts accordingly. One can also use other models to generate content-related tags, such as, for example, the existence of certain objects in the image. And even though these are soft tags, they may still be useful to approximate model performance across different conditions. For sensitive applications, we also recommend collecting important metadata through human annotation. Second, when creating cohorts, you may also want to prioritize for cohorts that have a high cost of error in the application. For example, in a credit risk assignment task, naturally the cost of mistake is very different for small versus larger loans, and this becomes a natural way of disaggregating model evaluation. In addition, then, one can also weigh the importance of errors in the reports by this cost. For example, a 20% false positive rate for smaller loans is equivalent to a 5% false positive rate for larger loans in this particular example. And doing this type of disaggregation is also informative when deciding what types of errors to fix next. Third, cohort size in the training data or test data may not always reflect real-world usage. Sometimes practitioners may find themselves in a situation when they have a reasonably small cohort in the data that has a high error rate. Even though the error rate is high, they are still not sure if this is a significant result because the test data itself is small. The recommendation here is that even though the cohort is small, it is still good practice to pay attention to the situation if the cohort is important enough for the application. For example, in the UCI income dataset, we see that the whole data has a low representation from races that are different than white. Naturally, every disaggregated evaluation on this dataset will have smaller cohorts for non-white groups, but this does not mean that the performance discrepancies that may be found in these cohorts should be ignored. Rather, it is a good idea to enrich the test data further or collect more of it. Finally, when designing cohorts for disaggregated evaluation, it is also possible to use either automated or manual discovery techniques. Automated methods are algorithmic or learning approaches that aim at best separating error cases from success cases in the data. Such methods are particularly useful if there are lots and lots of input conditions to deal with. The visualization that I'm showing here is taken from the Responsible AI dashboard, and it uses a decision tree to best separate error cases from success cases. Each path in the tree then becomes a cohort that can be described by using the same filters that are used in the tree path. For example, in this case, the visualization is showing that the error rate in the census dataset is higher for individuals that are married. They have an education number of years that is higher than 10 years, and they have a lower capital gain than 4.8K. Now, despite of the tool or the method that is being used for automated discovery, generally these techniques are good if you want to quickly discover cohorts that have significantly higher error rates. This means that if you were to take a decision on what parts of the data to put more focus on improving the model or the data, these would be good candidates to start with. Now, this does not, however, mean that these are the most important parts of the data or model to focus on from an ethical or application cost point of view. And that is why it is also a good idea to do some manual and explorative search on dimensions that are important for the application. For example, this other visualization from the Responsible AI dashboard shows how errors are distributed across the intersection of race and age for a model that was trained in the UCI income dataset. And this type of visualization can sort of show you what are the hit points where the errors are most concentrated across these two dimensions of interest. Now that we have introduced the main concepts of cohort definitions and design, the question is, what can I do next with the information coming out of a disaggregated evaluation? Indeed, the cohorts found with highest error rates can be used as starting points to go back to the training data or the model and understand what may be causing those errors. For example, one may find out, such as in this illustration, that the class imbalance for the problematic cohort may look completely different than class imbalance for the rest of the data. Or one may also be finding that there are other issues that are related to the problematic cohort, such as more noise or more missing values. In other situations, when debugging techniques are also empowered with interpretability methods, it is also possible to find out cases where the model for a particular cohort is using the wrong features or spurious correlations to make a prediction. Let's now move on to disaggregated model comparison. For evaluation, we mentioned that using a single score number is not sufficient because different cohorts may have very different performance. The same argument is valid when we compare models across different updates. A single score number may show that the overall model accuracy increases. However, if we visualize model performance in the form of a Venn diagram, where we intersect together the errors of the old baseline model with the new candidate model, we may notice that while some errors get fixed in the new model, the green region in this diagram, in other cases, new errors get introduced in the red region of this diagram. Ideally, it is preferable that the red region becomes as small as possible so that we do not lose user trust. We also want that this performance, if it declines or if it regresses, and sometimes this is unavoidable, it should not affect some cohorts more than others. In practice, there are many different reasons why incompatibility can happen during retraining, and this can be due to optimization stochasticity, changes in the training data, or the architecture of the model itself. No matter what the reason behind this is, in general, it is desirable with respect to model communication with users or with other components in the larger system ecosystem that we reduce incompatibility and make updates as compatible as possible with their previous selves. Related work has found that backward incompatibility happens sometimes at a concerning extent. For example, on experiments conducted with training the model with more data from the same distribution within the same model architecture, compatibility can be as low as 40% in this particular task of predicting mortality in the medical domain, which means that only 40% of the predictions that were originally correct are correct for the updated model, even though the updated model has a higher accuracy. Therefore, it is a good idea that along with accuracy scores, we also report compatibility scores that quantify the amount of expected compatibility issues that happen with the update. One way how to compute such scores is by using the backward compatibility in machine learning GitHub repository together with the associated Python package. Backward incompatibility sometimes impacts some cohorts more than others. This may happen when changes in the training data or in the model architecture may be more prevalent for these cohorts. Here we show a visualization taken from the Responsible AI Tracker Jupyter Lab extension. For the problem of predicting whether a house will sell for more or less than the median price, we see that increasing the number of estimators in a random forest generally increases model performance in the test dataset, but it decreases the performance on houses that are in a very good condition, higher than a score of 8 in this particular example. The disaggregated model comparison table then accordingly shows this decrease in the brackets as well as the overall increase for the whole test data. These types of reports enable a one-to-one comparison that highlights where and how a model improves, but also where it declines in performance. The report itself can be used during the process of model selection or when preparing updates that inform customers and users of the changes that have happened with the model. To conclude, a few takeaways from this video. Disaggregated model evaluation surfaces performance discrepancies across cohorts. Such discrepancies may have important implications in reliability, fairness, safety, and user trust. Disaggregated model comparison similarly ensures tracking of performance improvements or decline across cohorts and across different model updates. Compatibility during model updates helps maintaining trust with users or other components in the ecosystem. Disaggregated model evaluation and comparison are both useful as starting points to an informed and targeted model debugging and improvement process. Thank you for listening, and if you have further questions, do not hesitate to contact us at rai-toolbox@microsoft.com.